Hello everyone and welcome to day 11 of the 2024 Advent of Code. Let's get into today's puzzle. We're going to be using Python and today's puzzle is we have a set of stones, and every time we blink or every time we have one iteration of something, these rules are applied. So each stone has a number on it, and if the stone has a 0, it becomes a 1. If it's not that, then if the number of digits in the number is even, then we split it down the middle and put them to two separate stones. So say here, split it down the middle, and we got 10 and 0, so we don't keep any leading zeros. And if none of those apply, so this one's like highest precedence, then this one. If none, then we multiply it by 2024. Now, there is a line here about ordering preserved, but I'm going to talk you through a little bit here the sort of the way that I think you should approach this. I did originally do it with just a list, and sort of I would pop off the end one and make a new list, but it was way too slow. So I'm going to hopefully give you a few things here where it points us into where we need to go for the ultimate solution for this, which is to use the dictionary. So the first thing to note is that the history of this doesn't matter. So that the history of each stone doesn't matter. So if you get a number, say, this number here, if that came about by chopping another number in half or timesing a number by 2024, that doesn't matter how it got there. All that matters is the number. So there's no need to keep track of any history. So when we're doing this method over and over, there's no need to keep track of sort of previous iterations other than the iteration that you're on right now. Even though it does say about order being preserved, and order would be preserved if we were doing it in a list, but the order doesn't actually matter. So if you notice here, I've got two examples. I've got one starting with this and one starting with them flipped around. And the only thing we care about at the end of each of the iterations is the number of stones. So here you can see this gets multiplied, this 17 gets split up, this 0 goes to 1, and there's another iteration here, we end up with 5 stones. Even though these are jumbled around, you still end up with 5 stones. And we can do it on a slightly smaller level, that we can say, okay, each of the 3 operations either turns a 0 into a 1, which doesn't necessarily need any order or anything like that. It can turn a number into 2 numbers, and so this again, the order of this doesn't, the order of this and this don't matter. They're all only dependent on that one stone. And then similar to this first one, which is just adding 1, there's one that's times by that, and so every rule is only dependent on that one stone, and so the neighbors don't matter either. So there's really no need to keep any kind of list or order. And so we don't necessarily need lists, arrays. And one thing that we can do, which is the fourth piece just before we get into the actual coding, is it's a little bit wasteful to calculate what we need for this one, which is 2024, and also what we need for this one, which is 2024, because all of the ends, it's a function where something happens to these ends, but it's the only one input. There's no other input that can change this. This n will always end up being f of n, no matter where the n is. So to save doing loads and loads of computations, what we can do is just note down how many of these we have, and then we can do, so for this we could say, okay, there's 2 1s, so we know in the next one there's going to be 2 2024s. And so that sounds like keeping these as keys and the number, the frequency as values, which is exactly what we're going to do. So what we're going to do firstly here is I've just taken the example in, which is here, which was shown here, and it goes down like this. What I'm going to do is I'm going to create a dictionary. Because I've looked at this data as well, I know each of these just appear once. what I'm going to do is I'm going to say that our stones is going to be a dictionary where the value is the number. So each of these numbers, and so the key is each of these numbers and the value is the frequency of that. So I've got all the numbers here, and I'm actually going to make these all ints. I'm sure there are quicker or more fancy ways to do that, but that's just what I'm going to do. And then I'm going to say for n in numbers, I'm going to say stones n is equal to 1. And then if I was to print stones, I'm going to get int x for, with no spaces. So what I'll do is say split on the space. There we go. It's t stones. There we go. And so we get this 125 and 17, which each appear once. And then what we want to do is go through here and apply the rules. And if we have a frequency of 5, when we've worked out what this maps to, we're just going to find out what that maps to. So f of n, the output of this function, and have that frequency be 5. And so ultimately what we want is to have this blink, which takes in the original stones, or it takes in some stones and does it n times. And what that's going to do is going to say for index, which we don't care about right now, for index in range n blinks, stones is going to become this new function that we're going to make, blink once stones. And the reason we can keep writing over this every time is because the history doesn't matter. We don't need to keep a track of all the history. We just need this one and the next one. And then after we've done that n times, we're going to return the stones. Okay, and so our thing that we're going to calculate, final stones, is going to be blink, and we are asked to do this 25 times, or 22, 20, and 25 times, and then with the other input. But I'm going to do this for 6 times to show 22, 25 to show this number, and then I'll show you the output answer. So if we were to blink with the stones 6 times and print something related to this, and what are we trying to figure out? Well, each of the values represents 1 stone. Like if this was 2, that would mean there are 3 stones. So we want to sum up all the values. So we can go final stones dot values. Okay, and now let's make our blink once method. And so what we want to do is to create a new stones dictionary. And then we want to say for the stone and the frequency in stones. So this is just a nice way to get both the key and the value in one go. We want to say the first rule, if the stone or the number is 0, then we're just going to add 1. So add 1 stone of 1, or add frequency many stones of 1. Okay. And the way that we're going to add that many is that we want to take this new stones and go like this. 1 equals frequency. But 1 might not have been, well, we might get to 1 several times. And so we might not want to set it to frequency, we might want to add to it. And so what we can say is if 1, this key, is in new stones keys, so if it's been added before, then just increase it. And if it's not been added before, then this is going to be the first one. And this pattern here is quite usual when you have a key that you want to add into a dictionary and you're not sure whether that's a new key or a key that already exists, you just want to add to it. So that's the first of the rules. That's when the stone is equal to 0, which is this one. The next one says, okay, if the length of the stone is a multiple of 2, and in fact we want to go like this, so we want to turn it into a string, and then we want to do the length of that string, because, I'll show you here, if we do something like length of 5, that doesn't make sense. I'll show you here, length of 5, it breaks. But if we want to turn that into a string, then we know that string has a length. It has length 1. And that's exactly what we want. We want to find the ones that are even. And so we can say the length of the string of this number, if it's divisible by 2, then we want to do something. And that something is that we want to split the number in half and then add left stone. We want to add the right stone. And remember, we want to do that frequency many times. So to split the stone in half, what I'm going to say is I'm going to get the midpoint, and we know that it's even, so there will be a midpoint. We're not going to have a left and a right that are odd, like one even, one odd. They're going to be the same. What we can do is we can say to take the length, this thing here, and divide it by 2. That will give us the midpoint, and then we can get the left stone, which is going to be this. So I'm going to make something called parts. It's not strictly parts, but it's what I'm going to use here. It could be any variable here. And I'm going to say parts from the beginning up to this midpoint is going to be the left stone, and the right stone is going to be that midpoint up to the top. And this side is exclusive, so it doesn't include the midpoint one, and this one will include the midpoint one. And also these will be strings because we're taking parts of a string, and all of the stones need to be numbers, so we're just going to have integers. And then similar to how we did here with a key, adding it to this new stones, we're going to do the exact same thing, but instead of the key being 1, the key is going to be left stone, and then the key is going to be right stone here. Right stone here. And if this was in a larger application, you would take this out, because you can see we've got some repeated code here, and this is basically all just adding to a dictionary. And so we could have a function that has the key and value and the dictionary, and edits that. For now, I'm just going to leave it. And what I did forget to add is that each of these rules only apply once, so you wouldn't have something applied to the stone and then something else applied to the same stone. So we want to continue after we apply something, just like that. And then down here, once we're done, we're going to continue. And then if neither of these things happen, an alternative for these could be, you could have else's, but I'm going to write it like this. And then finally, we're going to have if neither of these things, then the new stone is just going to be the old stone times 2024. And so we're just going to take this that says for this key, so if the key, which in this case is going to be 2024, is in here, then add to it. If not, create it. And then after all of these stones have been through, we're going to return the new stones. And if I just do this once, so if I say print stones, after each turn, and I go, you can see here we started off with 125 and 117, and then we got 3 different numbers, which we can see here, 3 different numbers, and then here we can see 1, 2, 3, 4. Well, there's 1 here, 1 here, 1 here, 1 here, and then after 6 we've got 22, and that is exactly what we should be getting. And if we were to do it 25 times, and we won't print every time, we get this 55,312. And so then if we do it on the real data, and I'm not going to print out anything, we get this here, we get 211,306, which is the answer for part 1. And then moving on to part 2, it's one of those where it gives you a number to put in, and then for part 2 it says, okay, just give you a really large number. And for part 1 you could have done the implementation where you do take a list and you say you have a bunch of numbers and you pop off this one, apply the rules to it, add it to a new list, pop off this one, add it to a new list, and continue like that. But you start to run into, that's quite slow, because rather than, as we were saying before with those multiple ones, say, there's a case where there's multiple, say like with this 48 here, you do this work twice, whereas in this setup we only do it once. But also you can run into some memory issues, because these lists only get larger, potentially up to some point, but they're getting larger and larger with, with bigger numbers, and so you can run into memory issues. But this way it's much quicker, and so if I was to just change this to be 75, we get this huge number here, which you can see here ends in 283. And so yeah, hopefully you enjoyed that. Like I say, this wasn't my first implementation. Firstly I did with a list, and then popped off from the right, added to a new list, and then continued to do it. But it was taking, it'd get to maybe 30, 35 iterations fairly quickly, but then anything more, it was taking a long, long time, and there was no way it was going to get to 75 in any kind of sensible time. And also, I imagine at some point it would have just run out of memory and broke. So yeah, so this is how to do it. Today's puzzle, this is day 11. If you enjoyed, please do like the video. I'm going to be doing a video for every day, not necessarily on the day that the puzzle came out, but just when as soon as I can get to them. So yes, please like the video, subscribe for more, and comment if you've got any thoughts. That's great, and I'll see you all for day 12.